Hello, everyone. I'm Baoqing from Huazhong University of Science and Technology. Today, I'm very pleased to introduce our latest research, Hunter, an online cloud database hybrid tuning system for personalized requirements. It's well known that the performance of a database system can be quite sensitive to particular configurations of hyperparameter. However, because of the complexities of the database and the turning, such a task was done manually by database administrator for decades. Recently, many research have studied the potential of applying machine learning to enable automatic turning. Xing work mainly falls into two lengths, search-based methods and learning-based methods. The search-based methods use heuristic strategies to explore an ideal configurations in the search space. The learning-based methods improve exploration by building a model to learn from the historic behavior and experience samples. This paper is inspired by our recent experience in deploying these state-of-the-art methods in a real-world online cloud database environment and from our discussions with DBAs from Tencent. We summarize this as follows. First, availability. Most users expect the database system to be online during the turning process. We also observe the level of diversity in users' requirements that exists our exception. Different users may require different subspace for their turning tasks and can provide very different workloads. Knobs can be fixed or only be allowed to be adjusted in a certain range. For example, innovative hash index is equals off, and the thread handling is defined as pop threads only if connection is larger than 100. This can make the reuse of history data unavailable. As a consequence of the previous change, without any prior knowledge, we find that existing systems often fail to warm start the turning process. As shown in Figure A, the turning steps of state-of-the-art methods for optimal knobs on TVCC are 475 at least, considering the turning time in each step showing Table 1. This is nightmare for the user experiments. As a consequence of the code side problem, most existing methods require amount of time for workload execution. As shown in Figure B, the turning time of different methods for optimal knobs is 40 hours at least. We need to make use of clone CDB, such as parallelization, to reduce the turning time. Inspired by these challenges, we propose an online hybrid automatic turning system for CDB in this paper called Hunter. However, all the knobs turning methods can cause performance fluctuation during turning. To check the availability challenge, we avoid executing workload on the user's instance in each turning step. Considering that turning relies on the results of workload execution, it seems that the only solution is to implement the execution on a cloned CDB instead rather than the one that the user is using. In our cloud environment, each CDB is always deployed as a pair of instances, a primary instance which directly serves the user's request, and a secondary instance which acts as a backup. As a byproduct, this makes it easier for us to exercise the backup and create clone CDB. If we can clone one, why not more? So, to accommodate the availability challenge, we conduct explorations mainly on cloned CDB instances and only deploy the optimized configuration after the turning process. Facing the diversity of personalized requirements such as disabled knobs and adjustable range of knobs on different workloads, we find that transforming knowledge from history data over a different workload or a different search space to be incredibly challenging. It's really hard to train a model that can one fit all. As a result, one key decision that we made is to conduct online exploration for each user. Unfortunately, this poses a cold start challenge since our exploration needs to start from scratch. The cold start problem is sensitive to the quality of samples. The existing methods employ Latin hierarchical sampling or random sampling to select the samples. However, if the superior solution not in the current samples, the capture of optimal configurations is a tricky task, no matter what sampling method is used. Therefore, the generation of high-quality samples is prime. Genetic algorithm earns our trust because of its performance as shown in the left figure. The throughput of the genetic algorithm reads up much quicker than other methods, but it's lower at least. It uses less information, but it can concentrate more on developing samples with high short-term profits. The short quality of samples generated by genetic algorithm, given with 300 steps for turning on TBCC, will rank the samples by their performance in terms of throughput compared with that of 3 methods. As shown in the right finger, for the samples generated by different methods, genetic algorithm has the most high performance samples, which are much higher than those of other methods in the same segment. Genetic algorithms make full use of the similarities between high-performance parameters to learn quickly through crossover and mutation. Although it's difficult to find the optimal configuration at more steps, it can get superior samples in the preliminary stage. Now, let me detail the design of Hunter. It incorporates 2 learning models consisting of meta-heuristic algorithm model and a deep reinforcement learning model. Instead of rely on pre-trained model to warm start deep reinforcement learning, such as DDPG, Hunter employs a genetic algorithm to generate samples for DRL and to reduce search space with PCA and random forest. Besides the sample's quality, the data dimensionality is another factor influencing the DRL ratio because samples with high dimensionality may cause big search space for decisions. To reduce the search space, we refer to a term that comprises metrics and shifts nodes. PCA is a machine learning method that is commonly used to reduce the dimension of data. It transforms a large set of variable into a small set that returns most of the information. We select the random forest algorithm to rank the knobs. Random forest is a supervised machine learning method to deal with classification and regression problem, which can deem a voting algorithm consists of multi-decision tree used to calculate the importance of features. In fact, although the superior samples can help DDPG acquire better performance, it's hard to reduce the recommendation time without modification because DDPG as a DRL algorithm is difficult to correlate quickly. Therefore, with a large number of samples representing suboptimal solutions, we replace the exploration strategy of DDPG to fast exploration strategy. This improvement enables the model to select configurations with the best performance in the preliminary stage of turning and force the model to explore based on relatively better configurations. In addition, we optimize the system with multi-cloned CDBs to reduce the turning time. For example, our tuning process has 3 phases. In the first phase, each actor generates random configurations and stress tests them on the cloned CDBs. The results will be put into the shared pool. Sample factory takes these samples and use genetic algorithm to generate new configurations. The controller learns stress tests these newly generated configurations and produce the new samples in the shared pool. This process is repeated until the number of samples reaches a predefined threshold or the performance does not improve for an extended period of time. In the second phase, the search space optimizer collects statistics using all samples in the shared pool and conducts compression and shifting over metrics and loops. In the third phase, recommender acts over samples with reduced dimension and generates new configurations. Different from the sample factory, recommender uses DDPG instead of genetic algorithm. One key design decision in Hunter is to warm start the recommender using all samples generated by genetic algorithm in the shared pool. Similar to the first phase, these newly generated configurations are tested by controller until end. The controller then deploys configurations with the best performance on the user's instance. Our evaluation is implemented on two kinds of database, MySQL and PostgreSQL. In the experiments, we turned 65 logs and collect 63 metrics. Our experiments are conducted on 5 different workloads: Seedbench read-only, Seedbench write-only, Seedbench read-write, TBCC, and a real-world workload. We called it production. The details of our workload are shown in table 2. Shown in the table. Production is a real-world workload about business of education. We take the queries gathered at 4 o'clock a.m. at our workload and replay it concurrently to evaluate its performance in terms of the time cost. This is a read-write workload with about 200 tables and around 250 GB of data in total. To compare the performance of state-art methods, all methods start without any previous knowledge. And we have to mention that our method is called Hunter, and the Hunter star means Hunter with star instances. This figure shows the best throughput curves obtained by each method on different workloads. For the similar optimized throughput, Hunter is at about 2 times faster than that of the best one of other methods. Hunter 20 has the fastest speed to approach the optimized throughput in about 2 hours, which is about 20 times faster than that of the best one of other methods. And this figure shows the changes of throughput with a real-world workload drift. Figure A shows the changes. Figure A shows the curves of the best throughput changed on a real-world workload. For example, production collected from 9 o'clock a.m. obviously at the 8-hour mark. Hunter sees the lead and holds it to the 48 hours mark. At 48 hours mark, the workload drift occurs where the drifted production is collected from 9 o'clock p.m. As shown in figure B, all throughput reduced. However, the length-based approach can recover faster than the search-based methods. To further explain how Hunter produced the better performance, we compare the effect of each mode of a design on different workloads. We conduct our experiments on the different combination of DDPG, GA, PCA, RF, and FES. GA and FES make contributions to performance and recommendation time. PCA and RF can further reduce the recommendation time, as shown in the table. In this experiment, we explore the relation between the number of cloned CDBs and the benefits. For example, throughput and recommendation time. accommodation time to provide a reference for the number of instances in parallelization scheme. We conduct experiments on production, where the condition of the experiments are 1 instance 10 hours, 3 instance 10 hours, and 20 instance with 5 hours. The results are shown in the figure. According to these results, we believe that the parallelization scheme is conducive to all methods. Based on the hybrid architecture, Hunter can gain benefit from parallelization and achieve high performance faster with limited resources. Okay, that's all my talk. Thank you for listening.